SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 12, we will cover groundwater properties and flow characteristics. So, the different concepts that we will cover in this lecture are groundwater fundamentals, infiltration and soil characteristics, subsurface water, aquifers, and about groundwater flow and yield. So, let us first talk about the basics, which we, or this is a recap of what we have just discussed in the last lecture. So, infiltration is the entrance of rainwater or melted snow into the ground. Percolation is the movement of water after entrance, that means the movement of water inside the soil, and groundwater is the water that is stored in the ground as groundwater at a hard stratum. That means, the water cannot go further down, it is prevented by a hard stratum or an impervious surface, and that is stored in the soil as groundwater. So, as we understand, the water that is stored inside soil is also stored in the pores of the soil, and so this particular surface or this particular layer of earth which holds water, also known as the water bearing stratum or an aquifer holding water. So, these are natural storage reservoirs from which water can be withdrawn. So, this not only holds water, but also we can withdraw water from them. Then we also have something called a water table, which is the top of the water level in this particular reservoirs, that means in this particular aquifers. The level varies throughout the year and it rises in rainy season and gets depressed in summer. So, during rainy season the water level goes up and in summer it goes down. So, this is the level of water inside this aquifer, and aquiclude is the impervious stratum at which the water is being stored. This is known as aquiclude. So, these are the basics that we should know before we start talking about groundwater. Now, groundwater has got also certain other aspects that we should consider. Groundwater can sustain aquatic ecosystems. Some amount of bacteria and other kind of things could be found in groundwater. Groundwater flows may contribute to even 90% of river flow during dry periods. So, that means the amount of flow that we see in a river could be contributed not only from surface flows, but also subsurface flows, and that means groundwater contributes to even 90% of those flows. And only shallow groundwater is exploited, that means we do not exploit groundwater from very deep, even though technology allows us to extract from around even 500 meters depth. That means, we usually have deep tubules which can actually extract water to even beyond from 150 to 500 meters. So, but we should limit our groundwater extraction to only to shallow levels, otherwise we will have other problems that we will discuss. The image actually shows you the overall setting of an urban area. As you can see that this blue band in the image, this is the aquifer. This brown band is the impervious surface or the aquiclude, and this yellow area is basically the zone above the aquifer where we do not see, or you can see that this is the level which separates these two zones, and we can say this is the water table. That means, this is the water table, this is the level at which water is available. So, you can see the water level over here and the water level over here, these are different. Why? The reason is, over here water is being drawn, these are the pipes or the deep tubules or the wells which is drawing water from this particular area. Because you are drawing more water, the water table bends, right. So, this is why it looks like bended. Now, that means city authorities, urban authorities can get water for supplying water to an urban area, gets water from surface sources and also gets water from ground sources, right? And both of them goes for treatment, or some for treatment, some may not treat the groundwater, and some may directly in the treated water stream, they may directly charge the groundwater and then supply this particular water. And then this water supply is given to the different urban areas, that means either to buildings or to industry. And sometimes you see many of the urban buildings, like for example large complexes or industries, they draw groundwater themselves. So, this is they are drawing groundwater, but some amount of groundwater also comes back as recharge, because sometimes the buildings have got rainwater harvesting system, or they have got sanitation systems where the water is actually allowed to percolate from the wastewater, right. So, this kind of things, that is why you see grey water coming here, right. This actually is filtered while it travels through the sand and travels through the earth, and then actually gets into the groundwater. And finally, the water that is being used in the cities are disposed, and once it is disposed, sometimes it is retained at certain areas, and from there we, like, so for example an oxidation pond, from there some amount of water recharge also happens, and eventually water is disposed of. So, this is the cycle of groundwater, or how groundwater actually is being used, and along with of course surface water, and all of that is finally disposed, and it goes into the rivers from where it evaporates, and again the hydrologic cycle of water prevails. So, this is the basics of groundwater. And before we look into groundwater, we need to understand different characteristics of the soil and infiltration that determines how groundwater will be formed, or how groundwater flows within a particular area. So, first of all, we talk about infiltration. The amount of infiltration depends on definitely the rainfall characteristics of a particular area and also the soil characteristics. So, that means in case of very slow rate of rainfall, most of the water infiltrates into the ground. In case of heavy rains, less quantity percolates to the ground and more goes as runoff, because it takes certain time for the water to get inside the ground or percolate inside the ground. If you do not give that time, and if there is huge amount of heavy rainfall, then it actually goes as runoff. So, rainfall characteristics do play a role in the amount of groundwater that we get, and or amount of infiltration that happens. And similarly, soil characteristics also have a large role. For example, infiltration directly depends on the porosity of soil. If more porous, more percentage of sand, then more is the infiltration. Porosity of soil basically means the pores in the soil, right. And if the soil has got more pores, there is more chance of water getting stored there or getting inside, right. So, in case of sand, we see a lot of water can go inside, but it is not necessarily only the pores that is of our concern, because the size of particles is also important. For example, in case of clay, even though the pores is there is huge amount of pores in clay soil, but because these are so small in size, this actually is almost impervious. So, size of particle as well as the pores within the particles determine what kind of water will infiltrate, and eventually what kind of groundwater will be there in that particular area. So, both soil characteristics and rainfall characteristics determine the kind of infiltration and eventual groundwater in a particular area. So, how do we define porosity? Porosity is defined as the percentage of voids present in a given volume of soil or aggregate. So, it is expressed using this equation, where we have got total volume of voids in the soil in the top divided by total volume of soil. So, it is the percentage of voids in soil. So, if porosity is below 5%, then we call it small. If 5 to 20%, if it is, we say it is medium porosity, and it is above 20%, it is of high porosity, right. Ability of so, this is how we can say that the soil is highly porous or less porous, and so on. So, ability of water bearing stratum to store water, or ability of an aquifer to store water, depends on porosity and size of the particles. So, as we are discussing, it is not only the porosity, but also the size of the particles which play a role. And sand and gravel are the important aquifers for public water supply. So, obviously, sand and gravel are good aquifers from where we can draw a lot of groundwater. So, in this image you can see what I was talking about. This could be explained. So, you can see over here this is sand and gravel, it is highly porous, and these are unconsolidated. So, there is lot of gaps in between these particles, and these are of a larger size. So, there is enough space for water to be stored. So, in case of clay and silt, even though there may be, if there is low porosity due to cementation or presence of clay silt, in this kind of surface, if we have in this kind of soil, if we have also clay and silt, then automatically, even though this may be porous, but because of the small size, they will get filled up into these voids and eventually reduce the total amount of water that could be held in this particular soil. In case of rocks or stone, we can see this kind of voids created in the rocks, and you can see that low porosity consolidated crystalline rock due to presence of fractures. So, within the fractures of the rock, the water is stored, and this is a high porosity in fractured rock due to dissolution. That means some amount is dissolved. So, that is why more amount of space is created for storing water, such is in case of limestone. So, limestone can hold more water compared to other kinds of rock. So, let us see some of these values. So, sand and gravel have very fairly uniform size, and size as you can know that gravel is larger and up to 2 millimeter in size, and sand is a little bit smaller, but coarse sand is around 2 millimeter, fine sand is around 0.5 mm. So, when these are moderately compacted, we can see porosity levels of around 35 to 40%, right. So, this is the porosity level of compacted sand and gravel. Similarly, sandstone has got a porosity level of 14 to 30%, limestone of 5 to 17%, and clay of around 44 to 47%. So, you see clay is highly porous, but because size is 0.07 mm, so actually clay is almost impervious. So, this is something that we need to remember, that is not only porosity, but also the size of particles determine the amount of water that would be held in a particular aquifer or in the water bearing stratum. So, let us see how water is stored inside in the ground. So, this image actually shows the entire subsurface water. So, the topmost part is the unsaturated zone, or this is called the Vadose zone, and over here the water gradually infiltrates through this particular zone, and then the zone below that is saturated. That means we find that the entire pores are filled with water, and here we see that at this there is a division. The division is basically the water table. So, why is that water? What is the water table? Water table is basically at the level where the fluid pressure in the pores is same as the atmospheric pressure. So, that is why we see that at this level there is water available. So, this is the fluid pressure balances with the atmospheric pressure, which atmospheric pressure is obviously there is pressure. So, this is the level where it balances itself, and this is where we find the water table, right. So, this near the ground surface we see voids are partly filled with water and air. Of course, air pressure is also there. So, both water and air is there, and this is the unsaturated or Vadose zone, and movement of groundwater in this zone is slow, and residence time ranges from 0 to tens of years, depending on what kind of soil and other things. It could be it may be very fast, or it could be even tens of years that water will take time to reach from one zone to another. Whereas, at lower depths, that is at the saturated zone, and we see that the empty spaces are completely filled. So, that is why it is saturated, and here if we dig a hole or a well in the ground, it will be immediately filled with water from the surrounding area to a depth up to the water table. And as we are telling you, this is the level at which the water pressure balances, the fluid pressure balances with the atmospheric pressure. That is why if I can dig over here, so if you see that in many villages and all, people go and dig some of the river channels, and then they get water, or some of the areas they will keep on digging and then they get water because they do not have any surface water source. That means in any place they have to dig until this part, and then over here they will see water is accumulating, because the surrounding, this is the water level. So, they have to dig up till this, wherever till the water level, and then this is from where they can extract the water. The next concept is that of hydraulic gradient. Now, as we know that water is not only stored, but water also flows inside the ground, and this is determined by the hydraulic gradient. Or you can understand that if you imagine a surface joining the water level in many wells in a confined aquifer. Now, why it is called a confined aquifer? I will explain that a little bit later. Basically what it means, if I have got many wells, the water table, like in the previous slide, if I have a well dug over here, I will see the water level at this level. If I dig another water level over here, another well over here, the water level would be over here, right. So, it sometimes this level, if it is at a little bit distance, that water table may also vary, right. So, there we see that an imaginary surface joining the water level in many wells is in a confined aquifer. This is called the potentiometric surface. So, this is the potentiometric surface. As you can see, the water table is at different heights at different zones. So, if I dig a hole over here, a well over here, I will get water at this level. If I dig we will get water over here, right. So, hydraulic gradient is the difference between the levels of the potentiometric surface at any 2 points divided by the horizontal distance between them. So, that means the hydraulic gradient between these two places determines the flow of water. That means if this area is higher, this is lower, of course, water will flow in this direction. That means, water will pass like that, and then this flow is basically depends on the hydraulic gradient, that means the difference in between the levels of the potentiometric surface in both this location, and that determines the flow velocity and so on, right. So, over here you can see this is HA, this is the level at which water is available, this is the HB, and this is the impervious stratum, this is the reference plane, and divided by this distance, which is L, and we get delta H by L, which is the hydraulic gradient. So, this concept is very, very important when we determine flow of groundwater inside a particular surface. So, I was telling you about aquifers, confined and unconfined aquifers. So, in this image you can see that the first part is unconfined aquifer and the second part is confined aquifer. Why? See, this gray this thing is the impermeable base. So, over here we have a gray layer, which is the impervious layer, and that is why water cannot flow beyond it. So, that is why this is the water bearing stratum. So, this is you can call the saturated zone, but we have got also another impervious layer over here. So, what it means is this aquifer is confined because there is an impervious layer at its top, at above, whereas at this side there is no impervious layer and there is this is free. So, that means this particular aquifer is free or it is an unconfined aquifer. So, as you can understand that this is one concept. So, in the top is free of impervious overburden in case of non-artisan aquifer, and in case of confined or artisan aquifer. So, these are the two other terms that we use. Confined is known as artisan aquifer, unconfined is known as non-artisan aquifer, right. So, the other thing is you can also see the level of water table in this particular image, right. So, what you see over here is, here the water we have dug a well, and of course, the water table would have been somewhere around here, right, but we are now pumping the water out. So, obviously, the water table will bend around this point and it will form something called a cone of depression, which we will explain in a later lecture. So, this bending happens and you can draw water from here. In this particular case, exactly same, we can have a standard well, but over here you can see, because of the undulating surface of the earth, the potentiometric surface has gone above. So, that means here water pressure, water table is at a higher level. So, over here if I dig a well, you will see water automatically coming out. So, this is known as an artisan well, right. So, artisan wells are wells from which water flows automatically under pressure. Why? Because the water table is above. Hydraulic gradient line passes much above the mouth of the well, due to which hydrostatic pressure is increased, causing the flow of water. So, this kind of artisan wells are also possible, and we also need to understand what are confined aquifers and what are unconfined aquifers. Finally, we look into groundwater flow and yield. So, groundwater flow basically actually is the flow of groundwater that happens inside a particular aquifer depends on the hydraulic gradient of that particular aquifer, right. So, based on the hydraulic gradient, we can determine in which direction the flow will happen and at what rate the flow will happen. So, we usually find in gravel aquifers there is the flow is around 10 to 20 meters per day, whereas wells of good yield it is around 2 meter per day. So, in normal wells we find this is the rate of flow 2 meter per day, whereas in gravel aquifers it is around 10 to 20 meters per day. So, that is the flow of groundwater inside this particular aquifers. Now, groundwater yield, how much groundwater we can extract from a particular aquifer? It depends on, it is the quantity of water extracted by gravity drainage from a saturated water bearing stratum. So, saturated water bearing stratum is nothing but aquifer. So, based on gravity drainage means by normally if I just allow the water and if I allow the water to come out at one end, like for example, in this particular area if I allow because there is a slope, some amount of water comes out over here, right. Because of the slope, this is the water table and this is where it intersects with the ground. So, some amount of water starts coming out, right. So, because of gravity drainage, right. So, this is a spring, you can say. Similarly, and so how much water will come out? So, it depends on the amount of water that has been stored in the pores of the soil in the first place, but there is something also called retention. That means the pores of the soil also retain some value. So, even though there is gravity, because of gravity the water is coming out, some of the water will be held back by the pores, right, because of some certain interstitial attraction and so on. So, porosity is basically composed of two parts, one is called the specific yield and the other is specific retention. So, that means how much water would be retained inside the pores and how much water would be coming out of the pores, right. This together is the total volume of water that is being stored, which is nothing but porosity. So, specific yield is the ratio of volume of water obtained by gravity drainage to the total volume of subsoil. That means, if I do construct a well, how much water will come inside that well from that surrounding subsoil or surrounding aquifer. So, that is the specific yield of that particular soil, right. And specific retention or filled capacity of the soil is the ratio of quantity of water retained by the material against gravity drainage to the total volume of material of subsoil. So, this is the amount of water that will be held back inside the pores because of other attraction forces. Water held in the interstitial surface of particles is known as pellicular water. So, whatever drainage, even though you have a well, some amount of water will be retained in the surrounding soil. So, that is called pellicular water. So, this is so that is groundwater yield. So, this is the total volume of groundwater that we can actually get. So, this does not explain how much groundwater comes out, right. So, the next we look into two properties, two aquifer properties or characteristics of the aquifer. This is known as permeability, which is also known as the hydraulic conductivity, and the other is coefficient of transmissibility, right. So, what is permeability? It is the capability of a formation of soil to pass water through it. So, it is measured by the coefficient of permeability. So, depending on the characteristics of that particular aquifer, certain amount of flow or certain flow will happen at a certain speed within that particular aquifer, right. Of course, it depends on the hydraulic gradient, but it also depends on the characteristics of the aquifer. In some aquifer it is higher, some aquifer it is slower. For example, the rate of flow of water through an aquifer of unit cross sectional area under unit hydraulic gradient, that means for 1 unit hydraulic gradient. So, the more the unit hydraulic gradient, we will multiply with that hydraulic gradient, the flow will increase. But if I assume 1 unit hydraulic gradient and unit cross sectional area, for any unit cross sectional area that you take, how much water will pass through it, right. So, rate of flow of water through an aquifer of unit cross sectional area under unit hydraulic gradient. So, if this is a surface, this is the water table and water is this is the hydraulic gradient is towards this, water is flowing like this. So, if I can construct a unit cross sectional area, how much water will pass through it, right. So, that is what we determined at unit hydraulic gradient. So, we see that in case of clean gravel, the coefficient of permeability, which is given in centimeter per second, is around 1 and above. For coarse sand, it is about 1 to 1.01, medium sand 0.01 to 0.005, For silt, 5 into 10 to the power minus 1 to 1 into 10 to the power minus 5, and clay it is even less, 1 into 10 to the power minus 6. So, this is the centimeter per second, this is the speed of flow inside clay. So, you can see that in clay it is difficult for water to move, right. In silt it is difficult, but in gravel and all it is much more faster. So, in addition to permeability, which more or less determines the flow in this direction, if I try to determine how much water goes below, so that is determined by the coefficient of transmissibility, which is defined as the rate of flow of water through a vertical strip of the aquifer of unit width and full depth d under unit hydraulic gradient at a temperature of 60° Fahrenheit. So, we are mostly concerned with permeability, because we want to understand how much water enters into a well and so on, but sometimes we also need to determine the transmissibility. That means how much amount of water, at what speed, at what flow rate the water will go down after getting inside the soil. So, if that is required, we can go for coefficient of transmissibility, but otherwise for other determining yield of a well, determining yield of tube well, or for determining using groundwater as a source for urban areas, as a intake source for urban areas, we will actually be concerned with permeability in most times. So, this is the chart, this is a graph which shows the relationship, not relationship, it shows how for different particles or different kinds of soil like clay, silt, sand and gravel, how these 3 parameters vary, like for example, how porosity or characteristics vary. So, you can see porosity, which is around over here it is given like this 50% porosity. So, this is clay. So, even though it is 50% porosity, this actually shows us that for different, so this is the porosity actually decreases with gravel. So, in case of gravel the porosity is lower, right. But permeability, which determines the flow rate of water inside the soil, you can see clay has got much less permeability, because we already discussed the grain size is so low in case of clay. So, that's why it does not allow water to pass through smoothly, whereas for gravel and all the permeability is very high, right. So, even though porosity is lesser compared to clay, the permeability is much higher. And similarly, specific yield is how much amount of water that could be got out, that we can get from this from this aquifer. In that case, you can see for clay it is very less. It gradually increases from sand, and marginally decreases for gravel. So, more or less gravel and sand is more or less same. So, specific, this is the graph for this is the slope for specific yield is increases very high for sand and then gradually stabilizes. So, specific yield increases for sand and gravel, permeability is also high, that is why specific yield is high, but porosity is little bit less, but it is not that less, whereas clay, even though having higher porosity, but have got less specific yield and less permeability. So, to conclude, ability of water bearing stratum to store water depends on porosity and size of particles. Hydraulic gradient is the difference between the levels of the potentiometric surface at any 2 points divided by the horizontal distance between them. Groundwater flows following the hydraulic gradient and also depends on the characteristics of the aquifer. Then specific yield is the ratio of volume of water obtained by gravity drainage to the total volume of the subsoil. And permeability is the rate of flow of water through an aquifer of unit cross sectional area under unique hydraulic gradient. So, these are some of the references you can follow. Thank you.